So here in Chapter 17, we're going to be looking at carbonyl chemistry. And this starts a 6-chapter sequence where we'll be looking at different aspects of reactions with carbonyl compounds. In the first four, 17, 18, 19, and 20, we're going to be looking at reactions specifically at the carbonyl carbon. In chapters 21 and 22, we'll go into looking at reactions that are adjacent to the carbonyl carbon. So let's get started. So in this particular chapter, we're going to start with sort of the overview, and we'll look at different kinds of reactions, and we'll look at reactions with aldehydes, ketones, carboxylic acid derivatives, and carboxylic acids, and things like that. And then in the next chapter, we're going to get more specific, having to do with aldehydes and ketones. And in the chapter after that, we'll look at carboxylic acids and nitriles. And in the chapter after that, we're going to get into carboxylic acid derivatives. So let's start with the general structure and bonding. So there are two broad classes of carbonyl compounds. There are compounds that have only carbon and hydrogen directly bonded to the carbonyl, and those are going to include aldehydes and ketones. That will be part of the focus of this chapter, but that will be a primary focus of chapter 18. Compounds that contain only an electronegative atom in addition to the oxygen bonded to that carbonyl. That's going to include carboxylic acids, acid derivatives, esters, and amides. And we're going to discuss that in chapters 19 and 20. So let's talk about some of the features of a carbonyl. What makes it different than other kinds of functional groups? Well, first of all, the carbonyl carbons are sp2 hybridized, just like the carbons that we have in an alkene. So we've got the sp2 hybridized, which gives us a trigonal planar geometry around that carbon. And it's a double bond, so there's a sigma bond going to the oxygen. And there is also a pi bond going between the carbon and the oxygen. So in these ways, the carbon on a carbonyl resembles the carbon on a carbon-carbon double bond. However, there is an important difference, and this difference is what makes carbonyls so reactive. When we look at the difference in electronegativity between the carbon and the very electron-rich oxygen atom, we'll see that there is a significant partial positive charge on the carbon. And with that significant partial positive charge comes a lot of the reactivity. So that's going to be the main focus of what we do over the next few chapters. So in this very important way, we're going to look more closely at this polarity of the carbonyl group. So the very electronegative carbon, or the very electronegative oxygen atom on the carbonyl, means that is a polar bond, and that carbonyl is very electron deficient. The carbonyl carbon is very electron deficient. When we draw the resonance structures, we'll see that there's two resonance structures we can draw for every carbonyl, and that is one where we have the double bond between carbon and oxygen, and one where we kick out that pi bond to the oxygen, and we end up having a negative charge on the oxygen and a positive charge on the carbon. Now, the major contributor is the one with the double bond because it gives everything an octet. You'll see that this carbon only has 6 electrons around it, so it does not have a full octet. But even though this is a minor contributor, there is a significant partial positive charge on that carbon. And so we will find it's this electron deficient carbon that has a partial positive charge that gives carbonyl chemistry its unique features. So that's what we're going to talk about. So we want to look at two different types of reactions. we're going to look at reactions that do nucleophilic addition, and this is going to include aldehydes and ketones. So aldehydes and ketones, you can do nucleophilic addition across the carbon-oxygen bond, where you'll add a nucleophile to the carbon and usually a hydrogen, but it can be something else, but usually a hydrogen to the oxygen. And that is nucleophilic addition. This happens with all aldehydes and ketones, with a few minor exceptions that we'll get to later. When we have carbonyl compounds that contain leaving groups, usually some electronegative atom like oxygen or chlorine or nitrogen, then we have the possibility of doing nucleophilic substitution. So the big difference here is that with carbon and hydrogen, we get with carbon and hydrogen on aldehydes and ketones, we get nucleophilic addition, and with carboxylic acids, acid chlorides, esters, and amides, we can possibly get nucleophilic substitution. So we want to look at number 4 on the in-class assignment and determine whether these are going to undergo addition, nucleophilic addition, or nucleophilic substitution. Well, on this first one, we've got CH3, 2, and a carbonyl. That means that we have 2 carbonyls attached, or 2 methyls attached to that carbonyl. This is acetone, a commonly used solvent in organic chemistry. Well, that's a ketone. Ketones, we know, only do nucleophilic addition. So we will get nucleophilic addition to this particular one. All right, here we've got CH3, CH2, CH2, carbonyl, and then chloride. That is an acid chloride. Let's go ahead and draw it. All right, acid chlorides are in the category of things that undergo nucleophilic substitution. All right, here, this one is, say, CH3, carbonyl, oxygen, CH3. All right, that is an ester, and esters will undergo nucleophilic substitution. And then finally, we've got this one. We've got a phenyl group here, CHO. CHO is aldehyde. So this is benzaldehyde. And as we mentioned a little bit earlier, aldehydes undergo nucleophilic addition. All right, so aldehydes and ketones, nucleophilic addition. Here we've got an ester and an acid chloride, and those undergo nucleophilic substitution, those 2 in the middle. So let's look more closely at nucleophilic addition. We want to investigate what's going on with the nucleophilic addition. It is a 2-step process. In this 2-step process, the nucleophile will attack the electrophilic carbon. All right, so in that first step, it'll attack that electrophilic carbon on the carbonyl, and that will form this tetrahedral intermediate that has a negative charge on the oxygen. In the second step, we will protonate it with some sort of compound that's capable of protonating it, usually water, but it can be alcohol. And we protonate that, and we end up getting this alcohol. So that is our 2-step mechanism for a nucleophilic addition to either an aldehyde or a ketone. When it comes to how reactive are compounds to nucleophilic addition, so for aldehydes and ketones, we're going to find that there are 2 major factors. So we are going to break that pi bond. We'll make 2 new sigma bonds. But we'll find that aldehydes are more reactive to nucleophilic attack than ketones. And there's 2 reasons for this. One is for steric reasons and one is electronic reasons. Let's just look at the steric reasons first. With aldehydes, we have a hydrogen on there. Hydrogen is a very small atom. It's less bulky than any alkyl group, even methyl, making it very easy for a nucleophile to approach that carbonyl carbon. So the aldehydes are less sterically hindered. They're less crowded. That makes them more reactive. Ketones, because they have alkyl groups, they're both alkyl groups, those alkyl groups help to crowd out the nucleophile and prevent it from getting to the carbonyl, or at least slow it down. The other reason the aldehydes are more reactive is that anytime you have an alkyl group, the alkyl group adds electron density to whatever it is attached to. So in the case of the carbonyl, when we have an alkyl group like methyl or anything like that, it will add electron density to that electron deficient carbon, making it have a smaller partial positive charge, making it less reactive. So it stabilizes it and makes it less reactive. So for aldehydes, we don't get that stabilization, or we don't get as much stabilization because the hydrogens don't add that electron density. With ketones, we have two groups adding electron density, helps to stabilize them. So now let's compare this to nucleophilic substitution. In nucleophilic substitution, it's also a two-step process. And in fact, the first step is identical to the first step that we saw in nucleophilic addition. So the first step, the nucleophile attacks that electrophilic carbon on the carbonyl, which breaks our pi bond and creates this tetrahedral intermediate. That tetrahedral intermediate, remember in the previous mechanism, that tetrahedral intermediate got protonated. In this mechanism, what happens is that we have a leaving group, and that leaving group leaves, so the pair of electrons takes its pair of electrons, and then we reform the carbonyl, and we will get this new compound. This is called nucleophilic acyl substitution. So the big difference between substitution and addition is that in addition, we don't have a leaving group here, and in substitution, we do have a leaving group there. We'll find that the reactivity to nucleophilic substitution is going to depend on how good of a leaving group it is. So the better the leaving group is, the more reactive that particular compound is to substitution. So if we look at this reactivity chart here, we'll find that the least reactive is going to be the amides. And the reason for that is that our leaving group would have to be NH2 plus, or NH2 minus. Well, NH2 minus is a very poor leaving group. It's very difficult to make that as a leaving group. Now, there's some tricks we can use to get around that if we really want to, but it's a very poor leaving group. We'll find that carboxylic acids and esters are very similar in reactivity. We have a hydroxide or alkoxide as our leaving group, and so they're going to be somewhat more reactive, so somewhat more capable of leaving. And then finally, acid chlorides are going to be our most reactive. Now those are going to be our most reactive, and that's because chloride is such a good leaving group. With chloride being a good leaving group, it makes it possible for that substitution process to occur. So why is it that the aldehydes only do addition? Well, as I mentioned a little bit earlier, in the nucleophilic addition and in the substitution, they both have exactly the same first step. That first step is the nucleophilic attack of our nucleophile on the carbonyl carbon. So we get a nucleophilic attack there. And the difference is what happens to this tetrahedral intermediate. In the case of aldehydes and ketones, it's not possible to do this step where we have a leaving group. Hydride is a very poor leaving group, as is an alkyl anion that would also be a very poor leaving group. So since those are very poor leaving groups, this step where we have that act as a leaving group and get our substitution product is just not possible. So with aldehydes and ketones, we're essentially stuck forming, once we form this sp3 hybridized carbon, we're essentially stuck there. We can't go on and do our substitution pattern. So that is really what makes the aldehydes and ketones different. So now we want to talk about oxidation and reduction of carbonyl compounds. And the oxidation and reduction, whenever we do oxidation, that usually is going to include an increase in the number of carbon Z bonds, where Z is something more electronegative. Now, usually that more electronegative thing is oxygen, but it can be other things like halogens or even nitrogen. So just something that is more electronegative than carbon. If we increase the number of bonds to that more electronegative atom, we are going to oxidize. Reduction, and also we can decrease the number of carbon-hydrogen bonds. That will also work. With reduction, it's the other way around. If we decrease the number of carbon Z bonds or increase the number of carbon-hydrogen bonds, we're going to call that a reduction. So here you'll see that we've got one carbon-oxygen and we've got some carbon-carbon bonds and a carbon-hydrogen bond there. If we oxidize this, we increase the number, in this case, we increase the number of carbon-oxygen bonds by 1 by creating this double bond, and we've reduced the number of carbon-hydrogen bonds by 1. So this is an oxidized compound from this alcohol. We can go a step further and oxidize by breaking one of these carbon R bonds. So we can oxidize that and have a more electronegative atom there. So at this point, we've got 3 bonds going from carbon to something more electronegative. Now, there are a number of ways to do this, and we are going to look at some of them. Some of them will look familiar because we've seen some of these back in chapter 12 when we talked about oxidations and reductions. So our 3 most useful oxidation and reduction reactions are going to be the reduction of aldehydes and ketones to alcohols. We'll be looking at that in sections 17.4 through 17.6 coming up. All right. Reduction of carboxylic acid derivatives. So we can reduce a carboxylic acid derivative to either an aldehyde or all the way to an alcohol, depending on which reagent we use. And we'll look at that in chapter 17.7. We'll also be looking at the oxidation of aldehydes and alcohols to carboxylic acids. And we'll be looking at section 17.8 for that. So we've got some reductions, some oxidations, and so we're going to explore these and talk about them and look at mechanisms and things like that. So when it comes to reducing agents, our most commonly used reducing agents for aldehydes and ketones are going to be sodium borohydride and lithium aluminum hydride. Sodium borohydride, so there's the sodium borohydride right here, and then there is the lithium aluminum hydride right there. And there are some other metal hydrides that we will talk about a little bit later. There are some alternatives to these that are either less reactive or reactive in a different way. When comparing sodium borohydride to lithium aluminum hydride, I like to use this meme, and it's where we have the Doge and the buff Doge, where sodium borohydride is fairly mild, sort of like a family dog, and lithium aluminum hydride is very, very reactive. It's a very strong reducing agent, so like the buff Doge here. So I use this as a comparison just so you get the idea that sodium borohydride is very tame and lithium aluminum hydride is a very strong reducing agent. So when it comes to reducing aldehydes and ketones, we can use either sodium borohydride or lithium aluminum hydride. If we use the sodium borohydride, we do that with some alcohol. If we use lithium aluminum hydride, we do that and then follow it up with some water. But either one of these will work. However, sodium borohydride is usually a better choice for aldehydes and ketones because it is a less reactive reagent. It's easier to work with. The safety procedures for working with it are less rigorous. So I prefer using sodium borohydride unless I really need the lithium aluminum hydride. Either will work with aldehydes or ketones. Here is the typical conditions for sodium borohydride. You can take either an aldehyde or a ketone, treat it with the sodium borohydride in alcohol as our solvent, and we will get this alcohol. We'll get a primary alcohol as our product. If we use a ketone, we can also use sodium borohydride, but we can use lithium aluminum hydride if that meets our particular needs. We can use the lithium aluminum hydride. There we have to do a follow-up step where we use water and a second step. That will give us a secondary alcohol. So either of these will work. All right. Let's look at the mechanism for reduction of an aldehyde or ketone with lithium aluminum hydride. Keep in mind that sodium borohydride has a similar mechanism. So the very first step is that we get nucleophilic attack of our hydride on the carbonyl carbon. In doing that, we will create this tetrahedral intermediate. So we've created a new carbon-hydrogen bond in the process of doing this. And it will stay like that until, if we're using lithium aluminum hydride, it will stay like that until we add water to our mixture. When we add water, that water will protonate the alkoxide to give us this alcohol. So we do have to do that protonation to finish it off. So we have to add water. Conveniently, with sodium borohydride, the source of hydrogen is already there to protonate because we use an alcohol. So that saves us the second step. Now, you may be thinking, why don't we just put water in with the lithium aluminum hydride? Well, if you put water in with lithium aluminum hydride, the water will react directly with the lithium aluminum hydride, and pretty vigorously too. So it's best not to get the lithium aluminum hydride wet. So let's look at number 5 on our in-class assignment. So we'll go back over here to our document. And so the question is, what alcohol is formed when we treat each of these with sodium borohydride in methanol? So here we're just going to reduce this to the alcohol. So we just count the carbons, 1, 2, 3, 4 carbons. So our product here, 1, 2, 3, 4, and then OH, and that will be our alcohol that is formed. So if you're thinking, wow, this is really easy, it is. It's pretty easy. All right, if we reduce this cyclohexanone, all right, we'll create a secondary alcohol. We'll get cyclohexanol. Again, pretty easy reaction to do. Here we've got a ketone. We'll convert it to that alcohol. So we'll get that alcohol when we treat this with sodium borohydride. And that's it. That's pretty much what you need to know about these reducing agents. Now, it's going to get more complicated as we introduce more of these reducing agents and different options, but this is pretty much how it goes. So let's go back over to our presentation. Now, it is possible to do catalytic hydrogenation of carbonyls with hydrogen and palladium on carbon. We saw this back in chapter 12. So we introduced this ever so briefly back in chapter 12. And so that it is possible to take an aldehyde or ketone, treat it with hydrogen and palladium on carbon as a catalyst, and we can hydrogenate that to an alcohol. A very effective reaction. All right. You may recall that back in that chapter, we also found that we could reduce carbon-carbon double bonds with hydrogen and palladium on carbon. And so there's a trick we can do here. If a compound contains both a carbonyl group, so the carbon-oxygen double bond, and it contains a carbon-carbon double bond, which we'll see here on the next page, then we can get selective reduction of one functional group. So we can get selective reduction of one of those functional groups and not the other. And the way that we can do that is that we can, the carbon-carbon bond is more reactive to catalytic hydrogenation than a carbonyl. Alternatively, the carbonyl, we can reduce it selectively by using either sodium borohydride or lithium aluminum hydride. But in that case, the carbon-carbon double bond is completely inert. Or we also have the option of, if we use excess hydrogen in catalytic hydrogenation, we can reduce both. So it gives us the option of reducing one, the other, or both. And that is a very powerful tool. So let's look at an example. So here we've got the compound cyclohex-2-enone. All right. And with cyclohex-2-enone, there's two things that we could potentially reduce by that we could potentially reduce. We can reduce the alkene, or we can reduce the ketone, or we can reduce both. If we want to reduce just the ketone, we can use sodium borohydride to do that reduction, and we will create this allylic alcohol. So sodium borohydride reacts with aldehydes and ketones, but is completely unreactive with the alkene. So that's why the alkene remains intact. If we take this enone and react it with one equivalent of hydrogen using the catalytic hydrogenation, the palladium on carbon as a catalyst, we can selectively reduce the carbon-carbon double bond, and we'll create this ketone. And then this is the cool part, is that we can also do both. If we use excess hydrogen when we're doing the catalytic hydrogenation, we can reduce both the alkene and the ketone to an alcohol. And so that gives us lots and lots of options. Let's look at number 8 on the in-class assignment. All right, so here we've got number 8 on the in-class assignment. We've got this compound, which is CH3, carbonyl, CH2, CH2, CH, carbon-carbon double bond, CH2. So 1, 2, 3, 4, 5, 6. I'm going to draw it down here. 1, 2, 3, 4, 5, 6. And our second carbon has that carbonyl. And this last one has the carbon-carbon double bond. And so we'll just check again. So CH3, carbonyl, CH2, CH2, CH double bond, CH2. All right, so that is the structure that we're starting with. And we want to know what happens with each of these. Well, lithium aluminum hydride, that will do reductions of aldehydes and ketones. So in this case, it will only reduce that ketone to an alcohol. So our product, this alkene will remain intact, and we will get an OH group there. With sodium borohydride, we're going to get exactly the same product because it will only reduce aldehydes and ketones. It will not affect the carbon-carbon double bond. All right, here we've got one equivalent of hydrogen doing the catalytic hydrogenation. With that, we should only reduce this carbon-carbon double bond, so we will end up getting this ketone. All right, if we use excess, we're going to reduce both the carbon-carbon double bond and the ketone. So we will get this alcohol. All right, here we've got sodium borohydride, and we're using it in excess with CH3OH. Well, this is kind of a trick question, and the trick question here is that we're using excess. Well, that excess isn't going to do anything to this alkene, so it will simply reduce it to the alcohol, simply reduce our ketone to the alcohol. So we're going to get the same product that we did for parts A and B. So we'll get that alcohol. And finally, on this one's kind of interesting because in place of the hydrogen, we have deuterated sodium borohydride. And this probes whether you understand the mechanism of what's going on. This hydrogen is the one that acts as the nucleophile that's going to attack this carbonyl carbon. And then the hydrogen that ends up on the oxygen is going to come from this alcohol. So when we do that reduction, again, our carbon-carbon double bond is left intact, but we end up with deuterium instead of just regular hydrogen attached to that carbonyl, and then we will get hydrogen, regular hydrogen, attached to the oxygen. All right, so that is our differentiation between reducing a carbon-carbon double bond and a carbonyl. So here is just a quick example of using sodium borohydride in a couple of different synthesis applications. It's widely used in synthetic organic chemistry. This is a sort of a fundamental basic reaction that organic chemists learn. And in fact, many organic chemistry labs will use sodium borohydride reduction as part of their procedures that they use in their class. So here, sodium borohydride, we've got this ketone, and we can reduce that ketone to this alcohol. And then doing a couple of additional steps, adding a carbon in here and then doing an oxidation to give a carboxylic acid, we can get ibuprofen, which is a commonly used non-steroidal anti-inflammatory drug, or an NSAID, as they're commonly called. So over-the-counter medicine. All right, and then we can make muscone, which is it's an oil that is isolated from deer, but you can also make it synthetically. If we start with this compound, this ketone here, we can reduce that ketone. And then here it says 4 steps, and I don't know exactly what those 4 steps are, but clearly we break this bond and do some sort of elimination, and we end up getting this ketone. So, but the key feature here that we're emphasizing is that we can use reduction in synthesis. And this sodium borohydride reduction is a favorite of many chemists. So let's briefly look at the stereochemistry of carbonyl reduction. And so when we're looking at the stereochemistry, we need to have something where we're creating a stereogenic center. When we start with something like butanone, so butan-2-one, it is an achiral starting material. And I've mentioned this many, many times in my lectures and my videos, which is anytime you start with an achiral starting material and achiral reagents, you are either going to get an achiral product or a racemic mixture. And in this case, we get a racemic mixture. So here with the 2-butanone, when we reduce it, we do get a new stereogenic center. That carbon has OH, hydrogen, methyl, and ethyl all attached to that carbon. And so as a consequence, we have a new stereogenic center. But we'll find that the 2 products are equally likely. We will get an exact 50-50 mixture of the S-butan-2-ol and the R-butan-2-ol. So why is the product racemic? Well, the short answer for this is we started with something achiral and we put nothing chiral in there, and our only options are we either get an achiral product or a racemic mixture. But the reason behind that is that our carbonyl is planar, and so the hydride is equally likely to approach from either side. If the hydride comes in from the front side, so if it comes in from the front side, we will end up getting this intermediate. Once we protonate, we will get the S-butanol. And if it comes in from the back side, we will get this intermediate, and we'll get the R-butan-2-ol. So because they are equally likely, we'll get an equal amount of each. There's no reason why we would get one over the other. But what if you want to do enantioselective reduction? What if you want to pick a particular isomer that you're going to get more of, get an enantiomeric excess? It is possible to do that if you use the right kind of reducing agent. So here is an option that you can use. You need to have something that is enantioselective. So you need to have a particular reducing agent that can do what we call enantioselective or asymmetric reduction. It will preferentially send that hydride into one side or the other. And here are a pair of reagents that we can use. These are called CBS reagents. I'll talk about why we call them CBS reagents here on the next slide. But the example here is that we have the S2-methyl CBS reagent, the oxazoboroldine. I did not practice saying that one. Anyway, this is our CBS reagent, the SCBS reagent. Here is the RCBS reagent. You'll notice there's only one stereogenic center here. It's this carbon that is at this bridgehead. This one's S, this one's R, and then those are our CBS reagents. So why do we call these CBS reagents? And the reason that we call them CBS reagents is because they were invented, or they were developed by three chemists whose initial of their last names are C, B, and S. And so that's Corey, Bakshi, and Shibata. And these chemists developed these reagents to be used with aryl ketones. So if we have this aryl alkyl ketone, this one is acetophenone. If we use the SCBS reagent, we will get the R isomer of that alcohol. Conversely, if we use the RCBS reagent, we'll get the S isomer. Now, it's not so much that it always gives the S isomer, it gives this particular approach where the hydrogen comes in from the backside when you lay it out in this form. I mentioned that, and I'll show you on the next page an example where you have the R reagent and you get the R product, but it's because we changed the priority. So I'll explain it here in just a moment. So the boron hydrogen serves as the source of hydride in the reduction. And as I mentioned, if you use the SCBS reagent, you will get the R alcohol. If you use the RCBS reagent, you'll get the S alcohol as our product. But again, I think it's best to remember if it's S, you're going to get the hydride is going to come in from the front when you lay it out in this position. And if it's the R, the hydride is going to come from the back. Let me show you why I say that. Let's look at a different example. All right, so this particular example, it works the same way, right? So if you use the S is going to come in from the front of this, and we will get this hydride, which happens to be the R isomer. You'll notice that when we do this, we get 98.5% of this, 1.5% this. That is an enantiomeric excess of 97%. That is a huge enantiomeric excess. So it's very selective for getting this particular reagent. Now, if it just so happens that you need to get rid of this, like if you can't have any of this present, there are some separation techniques that you can use to separate enantiomers. It's complicated, but there are some techniques you can use. It usually involves taking this and attaching to this OH, attaching another stereogenic center. And that way you can create diastereomers, and the diastereomers are easier to remove. We'll talk about that later. All right, here is a synthesis example. And I like this example because it shows, well, it shows something important here. First of all, it shows the synthesis of a very useful drug, or at least part of the synthesis, where we use an enantioselective reducing agent. Since this is the R reagent, the hydride is going to come in from the back side and create this. Now, it just so happens that this is the R isomer. And the reason it's the R isomer is that we now have this bromine on there, and that bromine has a higher priority than the carbon that's over here. So we'd have oxygen, carbon with the bromine, carbon with that's attached to 3 more carbons. That's going to be clockwise. So this is the R isomer. Whereas, I'm going to go back. On this one, when we looked at this one, well, this is S. Let's go back one more. So here we have the R, hydride came in from the back. When we look at the priority here, the OH has the higher priority. The carbon that's in the benzene ring is second, and then the methyl is third. That's counterclockwise. This is the S isomer. So having the bromine on this changed the priority order, which is why we get the R isomer. So I think it's better, if you're trying to remember what does each reagent do, make sure that you lay out your aryl ketone where the benzene ring is on the left, your carbonyl is in the middle, and your alkyl group is on the right. And that for R, the hydride is going to come in from the back, and for S, it's going to come in from the front. And that's going to help you. And so, by the way, this drug is still in use. It's been in use for many decades. It's now often used in combination with an over-the-counter drug called Flonase, which you may have heard of, which is that's a steroidal nasal spray that people use to help with either hay fever or asthma, and they use that in combination to great effect to treat their asthma. Now, there are some biological enantioselective reductions, and I'm not going to go into great detail of this other than to say that there is a compound here. This is called the NaDH. So this is the compound. All right, so NaDH, and it's got this hydride right here. So it's got these 2 geminal hydrogens that happen to be a hydride, and you can use this as a reducing agent, but it only works in certain applications in cells, and you have to use a coenzyme. By itself, this doesn't do it. A coenzyme is an organic molecule that can function only in the presence of an enzyme. By itself, it just doesn't do it. So that involves quite a bit of extra work. If you have to have an enzyme in there, getting the enzyme can be tricky. So you have to use a particular enzyme to get your product. Now, there are all kinds of stereogenic centers here, so this one is selective, but it has to have that enzyme for it to work. Let me just show you a quick example of how it works. All right, so we'll find that the enzyme will bind to both the carbonyl compound and the NaDH and keep them in close proximity. How exactly that happens, I'm not even sure. I haven't seen any models of this, but I know that it's supposed to work. So it keeps them in close proximity and causes the hydrogen to go to one particular side of the carbonyl compound and to give you a particular reagent. And so you end up getting that reduction. So the NaDH donates that hydride, and it works very much the same way that other hydride reducing agents are. But this one, as I mentioned, works with an enzyme. So as far as how enantioselective, if you have a particular type of reaction, like you have a particular reaction that you want to do, for example, if you want to convert pyruvic acid into lactic acid. So here's pyruvic acid, which has a carbonyl directly adjacent to the carbonyl on this carboxylic acid. Well, we can do the selective reduction if we've got that and the lactate dehydrogenase, that's an enzyme, and it will give us just the S lactic acid. That'll be our only product. We will not get the R isomer of this. All right. You can do this with a variety of different compounds by choosing a particular catalyst, and you can get the R or the S by choosing a specific catalyst. So this is it's an involved process, and we're not going to get into other details of the mechanism other than to say that it's a way of doing enantioselective reduction. All right, there are some other metal hydride reducing agents that we can use. As we mentioned, lithium aluminum hydride, it is the buff doge, or it's a sledgehammer of reducing agents. It will reduce everything. To an alcohol, well, except for amides, and we'll talk about that. So lithium aluminum hydride is a very, very strong reducing agent. There are some less reactive reducing agents that we can use. One is called diisobutyl aluminum hydride, or DiBal. So DiBal has two isobutyl groups on it. So here's the diisobutyl aluminum hydride, and it is somewhat less reactive than lithium aluminum hydride. And the reason is because of these bulky alkyl groups. And because of that, we can do a certain reaction with DiBal that we can't do with lithium aluminum hydride. And I'll show that to you in a minute. Another one is this one, which is the lithium tri-tert-butoxy aluminum hydride. And because it has these electronegative oxygens bonded instead of just hydrogen, it affects the nucleophilicity of this hydride. And also the bulky groups, the bulky tert-butoxy groups help to decrease the reactivity of this. So it's also a less reactive nucleophile than lithium aluminum hydride. So how do we use these? Well, we can use these in specific use cases with acid chlorides and esters. So it's possible with acid chlorides and esters to reduce them to either an aldehyde or a primary alcohol, but it depends on which reagent you use. So here are the possibilities. If you have an acid chloride or an ester, you can reduce it just to an aldehyde if you use one of these milder reagents, or you can reduce it all the way to a primary alcohol if you use lithium aluminum hydride. So let's look at the specific cases. So the lithium tri-tert-butoxy aluminum hydride, that one will convert an acid chloride into an aldehyde, where of course the lithium aluminum hydride will take it all the way to a primary alcohol. This reagent will reduce it to an aldehyde, and this reagent doesn't affect the aldehydes, so it stops there. So it doesn't go any further. All right. Another example is with esters. So again, with an ester, if you treat it with lithium aluminum hydride, you can reduce it all the way to an alcohol, because that's what LaH does. All right. And if you take the DiBal and treat the ester with it, you can reduce it to an aldehyde. So this just gives us an option of selectively stopping at the aldehyde when we're reducing these two particular starting materials, either an acid chloride or an ester. And again, the acid chloride only works with this lithium tri-tert-butoxy aluminum hydride, and the ester only works with DiBal. Now, there are some other reagents that have been invented, but these are the ones that I want you to remember. So let's look at the mechanism of reduction of an acid chloride or an ester all the way to a primary alcohol. In the first step, we get nucleophilic attack. Anytime we have these reactions that we're talking about in this chapter or the next 3 chapters after this, our first step is going to be nucleophilic attack of our nucleophile at the carbonyl carbon to create our tetrahedral intermediate. Now, because these have a leaving group, the chloride or the alkoxy group, because they have a leaving group, we can have that leaving group leave, and we'll stop here at an aldehyde if we're using those specific reagents. But if we have lithium aluminum hydride, that will also react with the aldehyde to give another tetrahedral intermediate. And this particular tetrahedral intermediate doesn't have a leaving group, so we can't lose any groups here. And then finally, subsequently, we can add water to protonate that alkoxy group to give us this primary alcohol. So the big difference is LaH goes all the way through. So LaH, lithium aluminum hydride, is shorthand for lithium aluminum hydride. And the lithium tri-tert-butoxy aluminum hydride, it will react with the acid chlorides, and dibal will react with the esters. So let's look at number 10. All right, so here we go. Number 10, draw the structure of both an acid chloride and an ester that can be used to prepare each compound. So if we treat the acid chloride or ester that we're going to draw with lithium aluminum hydride, we will create these alcohols. And so it's very simple. Just draw that structure. And for the acid chloride, we'll do that. And again, we can, with LaH, we can reduce that to that alcohol. And then the ester, there are several options that we can use for the ester, but I'm just going to choose the methyl ester here. And that will work. And that's how we do each of these. So let's do this one. So again, just draw that skeleton. So 4 carbons there and 2 methyls on it. So 1, 2, 3, 4. We'll make that the acid chloride, and we'll put those 2 methyls on there. So that will get reduced to this with LaH. And 1, 2, 3, 4. We could do this ester OCH3. And again, we'll put those methyls on there to get the right thing. So these with lithium aluminum hydride will give us that alcohol. All right, finally, let's look at this particular benzyl alcohol. So if we made this a carbonyl and acid chloride, we would get that. All right, so that paramethoxy benzoyl chloride. And we could do this as an ester. All right, and that ester will give us this as a product. So now let's look at just a quick example of how one of these specialized reagents can be used with this. So here we have an ester, and this very complicated compound. So we have this ester, and if we treat this with lithium aluminum hydride, this ester will get converted into an alcohol. And in this particular synthesis, the synthetic chemist who were doing this wanted to create an aldehyde, not an alcohol here. And so to create that aldehyde, they used dibal to convert this ester into the aldehyde. And then with several additional steps, they can create this compound. And this compound is called ciguatoxin. So this is ciguatoxin. It's a particular compound that shows up in certain types of seafood and can be quite dangerous. So it's good to be able to synthesize these. One, because these particular compounds can sometimes be interesting starting points for other medicines. And in addition to that, it's good to have a sample of this that you can work with without having to go extract it from a bunch of fish. Anyway, interesting compound, and that is an interesting synthesis. Now, it's possible to reduce carboxylic acids all the way to an alcohol. And so if you have a carboxylic acid and you treat it with lithium aluminum hydride, it's going to go all the way to a primary alcohol. There's no way really to stop part way with lithium aluminum hydride. So lithium aluminum hydride, it's a very strong reducing agent. Remember, it's the buff Doge of reducing agents, and it will go all the way to the alcohol. There's no way really to stop it at the aldehyde stage because it's just so reactive. In order to do that, you really need to convert the carboxylic acid into either an acid chloride or an ester and use either the lithium tri-tert-butoxy aluminum hydride for the acid chloride or dibal for the ester. If you attempt to use a milder reagent on a carboxylic acid, it won't do anything. So carboxylic acids are a little tricky to go from that to an aldehyde. You have to make something in between. When it comes to doing reduction of amides with lithium aluminum hydride, we get something interesting that happens. So with lithium aluminum hydride and amides, we don't get reduction to an alcohol. And that's because our amide functional group, the NH2-, is a very poor leaving group. And so when we do this, we end up getting an amine, not an alcohol. So here is an example. So here is propanamine, and if we take propanamide, if we take propanamide and reduce it with sodium borohydride, we will get propanamine. So we do not get the alcohol, we get the amine. Now, we're going to take a brief look at the mechanism, which will help to explain why it is we don't get the alcohol. So here is the mechanism. This is a primary amine. Secondary amines work very similar. The tertiary amide rather. So this is a primary amide. Secondary amides work very similar. The tertiary amide has a slightly different mechanism, and you'll see the reason why for that in here in just a second. But first step, lithium aluminum hydride, in addition to being very good nucleophile, it's also pretty basic. So the lithium aluminum hydride will deprotonate that amide, create this, and this oxygen will then react with the aluminum hydride to give us this complex. And then the hydride will come in and act as a nucleophile on that carbon to give us this. And at this point, we don't get loss of the nitrogen group because it is not a good leaving group. Instead, we get loss of this, which has our original oxygen from over here, and we get an imine. And then the imine can get reduced using the lithium aluminum hydride. So the hydride comes in, we create our tetrahedral intermediate, and then protonate it with some water in a subsequent step to get this amine. So it makes it impossible to get the alcohol. Now, I'll mention this, for tertiary amides, these hydrogens are actually carbon, so we don't get deprotonation here. If we have a tertiary amide, we actually get that nucleophile going straight to the carbon, and then a couple of subsequent steps happen, but we still end up forming an imine in that step. So it's just a slightly different mechanism with tertiary, but it is a little bit different. So here is a summary of the metal hydride reducing agents. Lithium aluminum hydride, again, it's the sledgehammer of reducing agents. It will reduce aldehydes to alcohols. It'll reduce ketones to alcohols, carboxylic acids to alcohols, esters to alcohols, and acid chlorides to alcohols. With amides, it's a little bit different. It won't go to an alcohol. It will go to an amine. Sodium borohydride is a milder reducing agent. You can really only use it on aldehydes and ketones and reducing them to alcohols. But if you have these and you're trying to reduce them, sodium borohydride is the better choice. The other options were, if you have an acid chloride, you want to convert it to an aldehyde, you can use the lithium tri-tert-butoxy aluminum hydride to create the aldehyde. And if you have an ester, you can use the diisobutyl aluminum hydride or dibal to reduce the ester to an aldehyde. So that is a list of things. I want you to know these reactions. I'm not going to test you on the mechanisms for these reactions. What I'm going to test you on is to make sure you understand the reactions. So you don't necessarily have to reproduce the mechanism for this on the exam, at least for my class. Now, your professor, if somebody else is watching this, your professor may have different requirements, but I do want you to understand the mechanism so you can understand why stuff like this happens, why we get the amine here and not an alcohol. Let's look at 11 and 13, and after that, we're going to stop the video, and we'll have our second video. All right, so number 11. We want to draw the products formed when LaH, or lithium aluminum hydride, reduces each of these compounds. Now, this is pretty easy. If it's a carboxylic acid, an ester, or an acid chloride, it's going to become an alcohol. If it's an amide, it will become an amine. So this is a carboxylic acid, so we're going to get the alcohol from that. 1, 2, 3, 4, OH. So we won't have that carbonyl anymore, and we'll get these two methyls. 1, 2, 3, 4, 5, 6 carbons there. This is going to create the amine. So 1, 2, 3, 4, 5, 6, NH2. All right, here we've got another amide, and when we reduce that, we're going to get an amine. All right. And then with this amide, this is a special kind of amide. It's called a lactam. So when you have a cyclic amide, that's called a lactam. I'm going to put that down. We will talk about that in more detail in the chapter, I think it's chapter 20, what lactams are. And we will get that particular amine. All right, for the last one of this particular video, we're going to look at what happens when we use each of these reagents on this compound. Now, I've taken the liberty of drawing out this compound, and I'll go through it with you. So CH3, that's these two CH3s. Carbon double bond, so there's the carbon double bond, CH2, which is this one, carbonyl, which is this ketone, CH2, carbonyl, and you'll notice there's two oxygens there. That means it's an ester, and then CH2, CH3. So this particular compound is that. And we want to know what happens when we treat this with one equivalent of hydrogen with palladium on carbon. So we do the catalytic hydrogenation. Well, it's only going to affect this particular bond, because it will selectively do the alkene first. So 1, 2, 3, 4. All right, I got a little overboard there. So 1, 2, double bond there, and then this double bond will be hydrogenated. I kind of made it too big there. All right, so we'll only reduce that. With two equivalents, we'll reduce that alkene and we'll reduce this ketone, but we'll leave the ester unaffected. So let's see if I can get a little more space in here. 1, 2, 3, 4, 5. So our ester will remain unaffected, and then this will be an alcohol, and this alkene will get reduced down to the alkane. So we'll reduce two different things there. With this one, we have lithium aluminum hydride followed by water. Well, lithium aluminum hydride will reduce any carbonyl, so it'll reduce this this ketone and this ester. So 1, 2, 3, 4, 5, 6, 7, 8. So the ester is going to get converted into an alcohol. And the ketone is also going to get converted into an alcohol. But lithium aluminum hydride doesn't do anything to the alkene, so it leaves that completely unaffected. So we'll get this compound. And then finally, our last problem on this particular video is we're going to use sodium borohydride. Well, sodium borohydride will only affect aldehydes and ketones. So we have this ketone here. It will leave the alkene unaffected and this ester unaffected. All right, so that ester is unaffected. And our ketone is here. And that becomes a secondary alcohol. And then the alkene, like I mentioned, is unaffected. All right, well, in the next section, we're going to look at oxidation of aldehydes. And so we'll see you then.